Welcome to the second part of lecture 6, integrating Gaussian and Frullani integrals. The title is Miscellanea, Integrating for Experts. I'm going to be going over two different kinds of integrals that everyone should know about, but most people don't. And I hope that by going through this, you will be able to appreciate and understand some of the more complicated things that you can do with integration. So we'll start with the Gaussian integral. This is an integral that everyone should be familiar with. You certainly should have seen it somewhere in your calculus classes or in your physics classes before this. And it simply says the integral from minus infinity to plus infinity dx of e to the minus x squared is equal to the square root of pi. And the first thing you might ask is, what in the heck is going on with a square root of pi? Where does something like that ever come from? And it turns out the derivation of the Gaussian integral is rather simple. It requires a clear thinking outside of the box and taking a look at very different ways of approaching integration and approaching integrals. And in order to go through the derivation, which really will only take one page here, we're going to call that Gaussian integral, the integral dx e to the minus x squared, we're going to call that integral I. And then the square of I is just the repeat of that integral, but I'm going to use two dummy indices, one called x and one called y, so I have an integral dx dy, and here's where the trick really comes into play. When I multiply the integrands together, I can express it in terms of a sum of the arguments in the exponent. So I get an e to the minus x squared minus y squared. Now, if I was giving you this integral to integrate, the first thing you might think is, well, maybe I should try polar coordinates. And that would indeed be a really good idea. So let me just refresh your memory about how we go from Cartesian to polar coordinates. Dx dy is equal to dr r d phi. And so the integral becomes the integral from 0 to infinity. R only runs from 0 to infinity, and an integral from 0 to 2 pi over phi, because phi runs around the entire circle. And then we have this factor of r that is coming from the integration measure. We have a e to the minus r squared because x squared plus y squared is equal to r squared. And we have an integral over phi, an integral d phi. Now, there's no other phi dependence in here, so that's just an integral over d phi of a constant. I can immediately do that integral and I get a 2 pi. And I'm left with this integral from 0 to infinity dr r e to the minus r squared. Well, this is just perfectly set up for using our inverse chain rule. We set u equal to r squared, and then du would equal 2r dr. This then becomes the following. I squared is equal to pi, the integral from 0 to infinity, du e to the minus u. That's an exponential. We can just integrate it. The integral of e to the minus u is just minus e to the minus u. So I get minus pi e to the minus u evaluated from 0 to infinity. At infinity, that integrand is equal to 0. And at 0, that integral is equal to 1. So I get pi. Of course, that's equal to I squared. So I just have to take a square root, and I get I is equal to the square root of pi. So I just want to re-emphasize there are two key tricks here. One is to note that if I square the integral, I can convert from Cartesian to polar coordinates. And the other was to use the inverse chain rule to complete the integration. All right, let's move on to Frullani's integral. While many of you have probably seen the Gaussian integral, I doubt anyone in this class has ever seen Frullani's integral. It's really quite a remarkable result because it works for any function. The only issue is that the integral itself has to be well defined. So the function has to decay as we approach infinity fast enough so that the integral is well defined. But as for any function that does that, then Frullani proved this following result, which is really quite spectacular. So I have an integral from 0 to infinity dx, f of ax minus f of bx divided by x. And that can actually be integrated for any f. The answer is f of 0 minus f of infinity times the logarithm of b over a. And first time I saw this, I was really shocked that you could get such a result. this derivation uses very similar ideas to what we did with the Gaussian integration, although it's not going to actually be squaring the integral. Instead, what it's going to do, it's going to recognize that you can generate this integral from a two-dimensional integral, and then there are two different ways that we can evaluate the two-dimensional integral, and that will then give us this Frullani form. So let's start with the double integral that is the kickoff point for all of this work. What we do is we have an integral from a to b dx, an integral from 0 to infinity dy, minus the derivative of f of xy, and that prime indicates a derivative with respect to the argument. So it's not a d by dx, it's not a d by dy, it's a d by dxy. Okay? Now, the integral over the first integral, and we're going to take this to be the integral over y, is actually trivial because the derivative with respect to the argument can just be written as x times the derivative with 1 over x times the derivative with respect to y. And if I have an integral dy of some function that's a derivative with respect to dy, then that integral just becomes the function itself evaluated at the two limits. So the first integral over y simply becomes minus f of xy divided by x, evaluated between 0 and infinity. So let's go ahead and evaluate it. Remember, it's y that is going to be evaluated between 0 and infinity. So f of x times 0 is equal to f of 0, and f of x times infinity is equal to f of infinity. And so we get this term, f of 0 minus f of infinity, divided by 1 over x. Now the integral over x is relatively simple to do. It's just a logarithm. So I'll get the logarithm of b over a that's going to multiply that. Okay, this is giving us the right-hand side of the Frullani integral. So you might suspect that the next step is going to be instead to do the integral over x first. And that is indeed what we're going to do. And that's going to give us the left-hand side of the Frullani integral. So once again, we'll write this out. We're going to now do the integral over x, and remember, the derivative with respect to the argument can be written as 1 over y, the derivative with respect to x. I now have something that's a d by dx of some function, and I'm integrating it dx. That integral just will give me the function evaluated at the two limits. Because of the minus sign, it ends up giving me f of a times y minus f of b times y rather than the opposite order. And it's divided by y because that came out when I take the derivative with respect to x as opposed to the derivative with respect to xy. And the only thing I have to do to get the Frullani integral is I have to change that dummy index or dummy integration variable y into a dummy integration variable x, and then you see we've established this Frullani integral. So we've proven Frullani's integral holds, and I'll just refresh your memory once again about what it is because we're on a new page here. And let's take a look at a couple of examples. So the first example is an integral e to the minus ax minus e to the minus bx over x integrated from 0 to infinity. If I recognize that that's a Frullani integral with f of x equal to e to the minus x, then e to the minus 0 is just equal to 1, and e to the minus infinity is equal to 0. So I'll get 1 minus 0 log b over a, which is just log b over a. Another example here is an integral b sine ax minus a sine bx over a bx squared. And for here, we have to recognize that this is a Frullani integral for f of x equals sine x over x. If we do that, then you can find that indeed, by evaluating sine x over x at 0, where it's equal to 1, and evaluating sine x over x at infinity, where it's equal to 0, you can see that you're going to get the log b over a again, and then you have to do a little bit of algebra to verify for yourself that f of ax minus f of bx is equal to that form. Recall f of ax would be sine of ax divided by a, and I can write that as b sine ax divided by ab. There's also an x in the denominator, and then there's an extra x in the Frullani definition, which is why this denominator is equal to x squared. And if I do the same thing for f of bx, I would get sine bx divided by bx, which I can write as a sine bx divided by abx. And then once again, there's an extra factor of x that comes from the definition of the Frullani integral. So I just want to point out this is an integral that very few people seem to know. It doesn't come up very often in physics, but on the occasion that it does, it's really useful to be able to remember that this is actually an integral that can be exactly integrated, and it's one that just requires you to recognize what is the f in this Frullani integral form.